Welcome, class. Today, we're diving right into the language the universe actually speaks. We're going to explore the essential guide to the core branches of physics. Consider this explainer your ultimate starting point. We're going to walk through all 9 essential branches clearly, concisely, and most importantly with real-world context. Now, if you're coming into this with zero prior knowledge, you might look around and ask some pretty fundamental questions, like why exactly does a ball fall to the ground? Or why does a magnet suddenly snap to a piece of iron? Why does the sun keep shining day after day? Well, physics is, at its heart, the science of why. And the beautiful truth here is that every single answer traces back to just a handful of foundational principles. These are the physics fundamentals that literally underpin all of science and technology. You see, physics is far more than just an academic subject you memorize for a test. It really is the language the universe speaks. Think about it. The smartphone in your hand, the electricity running through your walls, the GPS guiding your drive. All of those things only exist because someone, somewhere, understood a fundamental law of physics and actually applied it. Mastering these fundamentals doesn't just give you a deep understanding of nature, it builds a problem-solving mindset that you can transfer across literally every single field of science and engineering.
All right, here's our syllabus for today's explainer. We'll start off with everyday forces like motion, heat, and waves. Then we'll transition over to electromagnetism, scale all the way up to the modern and cosmic levels, and finally wrap up with a quick recap. Let's get right to it.
Section 2. Motion, heat, and waves, everyday forces and energy. We're going to start with the branches of physics that govern the tangible world, the stuff you can actually see and feel around you every single day. Mechanics is really where physics begins. It's the study of motion, force, and energy, completely governed by Newton's 3 laws of motion. The key concepts you'll run into here are velocity, acceleration, momentum, work, and gravitational force. And take a look at this elegant equation, F equals ma. It perfectly connects force, mass, and acceleration in just one simple statement. This single branch of physics dictates everything from calculating the exact trajectory of a flying cricket ball to designing the suspension system of a car. Next up we have thermodynamics. So this is the study of heat, temperature, and energy. It fundamentally determines what is physically possible in our universe, which actually includes the fact that no engine can ever be perfectly efficient. Real-world applications for this range from your kitchen refrigerator and massive jet engines to global weather systems and, yep, even the human body. Thermodynamics also introduces one of the absolute most profound ideas in all of science: entropy. That's essentially the universe's natural tendency toward disorder. Moving right along, let's talk about waves and sound. Waves are super fascinating because they carry energy without actually transporting matter. There are 2 main types you really need to remember here. First, sound waves, which are longitudinal mechanical waves that absolutely require a medium, like air or water, to travel through. And second, electromagnetic waves, like light, which don't need any medium at all. This brilliantly illustrates the Doppler effect. You've definitely experienced this when an ambulance siren changes pitch as it speeds past you. And in medicine, wave physics is the exact principle behind things like ultrasound imaging and sonar. Now, closely related to waves are oscillations. An oscillation is simply any repetitive motion about an equilibrium position. The most fundamental form of this is simple harmonic motion, which is described mathematically by Hooke's law, F equals negative kx. Just think of pendulums swinging, vibrating strings on a guitar, or alternating electrical currents. This branch also explains resonance, which happens when a system is driven at its natural frequency. Resonance is exactly why musical instruments produce such beautiful sounds, but it's also the reason why some bridges and structural engineering failures happen. Moving on to Section 3, electromagnetism and optics. Light, power, and circuits. Let's see how all of this builds into the invisible forces that power our modern electrical world and literally shape how we see. Electromagnetism is an absolutely massive breakthrough because it unifies 2 forces, electricity and magnetism, into a single framework. And that framework is described beautifully by Maxwell's equations. Literally every electric motor, generator, radio signal, and light wave is a direct product of these principles. For your everyday electrical circuits, Ohm's law, or V equals IR, is the governing rule. Even the speed of light itself emerges from electromagnetic theory. It's truly the backbone of modern electrical engineering and communications technology. Then we have optics, which is the physics of light and vision. It explains exactly how reflection and refraction work, as well as the behavior of lenses and mirrors. It also extends into wave optics, where we see light interference and diffraction, which reveals that light actually has a wave nature.
So from the eyeglasses on your face and the cameras in our phones, to fiber optic internet cables and advanced laser surgery, optics shapes how we see and communicate with the world.
Next up is Section 4, the modern and cosmic scale, atoms, computing, and the universe. Now, we're going to look at the revolutionary physics of the early 20th century. These are the big ideas that completely rewrote the rules at both the smallest microscopic scales and the largest possible cosmic scales.
Modern physics really consists of two revolutionary ideas. First, we have Einstein's theory of relativity, which revealed that space and time are actually flexible. This gave us E equals mc squared, proving that mass and energy are completely interchangeable. Second, we have quantum mechanics. This showed us that at the atomic scale, particles behave in highly unpredictable ways that classical physics simply cannot explain. Together, these two mind-blowing ideas gave humanity nuclear energy, lasers, and MRI machines.
And when we apply quantum physics and electromagnetism to control electric current through semiconductor devices, we get electronics. The invention of the transistor back in 1947 was the spark that triggered the entire digital revolution. Today, you've got billions of transistors sitting on a single silicon chip just to power your computer or your smartphone. They use logic gates to perform Boolean operations, which are the absolute foundation of all digital computation. So, understanding basic electronics is pretty much essential for anyone pursuing computer science.
Astrophysics applies all of these branches to the grandest possible scale we have. We're talking stars, galaxies, black holes, and the universe itself. It asks massive questions. How do stars generate energy? What actually happened at the Big Bang? We use incredible tools like the Hubble Space Telescope and gravitational wave detectors to peer out into the cosmos. But here is a truly mind-bending fact to consider. Roughly 95% of the universe is made up of completely unknown dark matter and dark energy. Only 5% is the normal matter that we actually understand.
That brings us to Section 5, how physics branches connect, unified applications in the real world. What's truly fascinating here is that no single branch of physics stands alone. Let's look at how this interconnectedness works in the exact technologies we rely on every day.
Take GPS satellites, for example. If you want to know your exact location on a map, your phone's GPS is relying on mechanics to accurately track satellite orbits. But because those satellites are moving incredibly fast and are further away from Earth's gravity, they also have to use Einstein's relativity to make tiny, precise timing corrections to the signals. Without combining classical mechanics and modern physics, your GPS would basically be useless. A medical MRI machine is another absolute masterpiece of unified physics. To look safely inside the human body, an MRI blends the quantum mechanics of atoms, incredibly powerful electromagnetism, and precise wave theory, all working at the exact same time. Once you learn the core branches of physics, you unlock the ability to comprehend incredibly complex modern technology just like this.
And finally, Section 6, recap and practice questions. Let's test your understanding. Before we finish up our class today, let's do a really quick recap and test your knowledge. This is especially useful if you're prepping for competitive entrance exams like JEE or NEET, where having a strong grasp of these fundamentals is absolutely essential.
So, the most crucial point to remember here is the difference between classical and modern physics. Classical physics, things like mechanics, thermodynamics, and electromagnetism, works perfectly for everyday objects moving at normal speeds. However, modern physics, meaning relativity and quantum mechanics, has to step in when we're dealing with phenomena involving very high speeds, strong gravity, or tiny subatomic particles, where those classical rules just completely break down.
All right, let's test your understanding with a quick practice question. Based on everything we've broken down step by step today, think about this. Which branch of physics should a beginner start with? Which one gives you the mathematical and conceptual foundation to confidently approach all the others?
If you guessed mechanics, you're right. Mechanics is your absolute starting point because it deals with everyday concepts you already intuitively know, like motion, force, and energy. It lets you build your analytical thinking and your mathematical foundation on tangible things you can actually see moving around you before you move on to the invisible forces of electromagnetism or the abstract concepts of quantum mechanics.
Whether your goal is to ace a board exam, crack a competitive test, or just satisfy a deep curiosity about the universe, investing in these fundamentals really reveals the deeper layers of how reality works. The universe follows rules, and physics teaches you what they are. So once you master the rulebook of reality, what new mysteries are you going to uncover next? Keep questioning, keep learning, and we'll catch you in the next explainer.